Bismillahirrahmanirrahim. Dear students, so let's discuss the problem for this week, and this problem is related to a double overhang beam. You can see that we have an overhanging part right at the beginning of the beam, and similarly there is another overhanging part on the other extreme end of the beam. There are 3-point loads acting, 5 kilonewton at point A and another 5 kilonewton load at point D and a 10 kilonewton load at point F, and there is a point moment acting at point C in clockwise direction with a magnitude of 10 kilonewton meter. The beam has two supports, one hinge support and one roller support, and all the spans are given to us. For the solution of this beam, our first step will be to determine the reactions of this beam. So let's apply the conditions of equilibrium and calculate the reactions. We have two reactions in this case, a vertical reaction at support B, RB, and a vertical reaction at support E, RE. First of all, let's apply sigma Fy equal to 0 with the convention of upward forces taken as positive. -5 is this first point load, then plus RB acting in the upward direction, then this -5 kilonewton force acting in downward direction, and plus RE acting in upward direction, and -10 kilonewton load acting at point F in the downward direction. If we rearrange this equation, we get RB plus RE equal to 20, and we can label this equation as equation number 1. Then let's apply the second condition of equilibrium. For this, we can choose point E. So sigma ME equal to 0, and our convention is clockwise movement will be taken as positive. 5 into 9, so this 5 kilonewton force, it is producing movement about point E in counterclockwise direction, so it will be taken as negative, -5 into 9. Then RB is producing movement in clockwise direction and lever arm is 6 meters. Then the point movement with plus sign because it is in clockwise direction and magnitude is 10 kilonewton meter. Then the other point load acting at point D, that's producing movement in counterclockwise direction and it has a lever arm of 2 meters. And RE is passing through point E, so it will not produce any movement about point E and it will not show up in this equation. And then the last force, this 10 kilonewton force acting in downward direction, and it will produce clockwise movement about point E, and that is equal to 0. So if we rearrange this equation, we can get the value of RB and it comes out to be 2.5 kilonewton. And when this value is plugged in into equation number 1, we will get RE equal to 17.5 kilonewton. So in this way, we have got the values of both the reactions, RB and RE. Next step is to divide the beam into portions, and we know that we consider a separate portion whenever there is a change in loading or there is a change in the boundary condition or support of the beam. So we start from point A. At point B we have a hinge support and a reaction, so AB will be our first portion. Then B to C, at C we have a point moment, and then C to D, because at D we have a point load. Then from D to E, at point E we have support, so this will be a dividing line between the portions, and then the last portion is portion EF. So it means that for this beam we will have to consider 5 different portions: AB, BC, CD, DE and EF. Now let's consider these portions one by one. So portion AB, is from 0 to 3 meters, and here is the free body diagram of portion AB. This is free end, it's point A section, and these are exposed forces, shear force in the downward direction and moment in counterclockwise direction. The X will start from extreme left end. One particular reason of selecting this problem for this week is that some of the students get confused when they see overhang portion at the beginning, because they assume that the X should always start from a support. So I want to clarify that that that's not the case. In our case, we will always consider x starting from the extreme left end, whether there is a support or not. So x is starting from this point. Now we can simply apply the conditions of equilibrium to get the equations of shear and moment. Sigma Fy equal to 0 with upward forces as positive. 5 kilonewton force is acting in the downward direction, so minus 5, and V is also acting in the downward direction, so minus V, and this gives us V equal to minus 5 kilonewton. There is no x involved in this equation, which means that the value of shear is constant for the entire portion. Next is the equation of bending moment. For that, we'll take sum of moment about the section, sigma mx equal to 0, with the convention clockwise moment as taken as positive. 5 kilonewton force will produce moment in counterclockwise direction about the section, so minus 5x, x is the lever arm, and this m is producing moment, m is in counterclockwise direction, so minus m, and if we rearrange this, we get m is equal to minus 5x. X is present in this equation, which means that the value of the moment changes with the variation in x. So we will calculate the value of moment for point A and point B. At point A, x is 0, so MA comes out to be 0, and at point B, x is 3, and MB comes out to be minus 15 kilonewton meter. Now we are getting 0 value of moment at point A. Is this logical? If you look at point A is a free end, and there is no point moment acting at this free end. And we have discussed this earlier, that if we have a free end and there is no point moment acting at that free end, the bending moment will be equal to 0 at that free end. So the 0 value of bending moment at point A is logical. Next portion is portion BC. The range of x for portion BC is 3 to 5 meters. Here, starting from this point up to this point, so it is 3 to 5 meters. And this is the free body diagram of the entire left side of the beam. We have a hinge support here, point load 5 kilonewton acting in downward direction at point A, and we have a support reaction 2.5 kilonewton at point B. This distance AB is 3 meters and we have exposed shear and bending moment. Let's apply the conditions of equilibrium. Sigma Fy equal to 0 first. 5 kilonewton is acting in the downward direction, so minus 5 plus 2.5 in the upward direction, and then minus V. And if we rearrange this, we get V is equal to minus 2.5 kilonewton. Then sigma mx equal to 0 with clockwise movement as positive. So this 5 kilonewton force is producing movement about the section in counterclockwise direction, so minus 5x, and then this 2.5 kilonewton force acting in the upward direction is producing movement in clockwise direction about the section, so plus 2.5 into x minus 3. How did we get this x minus 3? The distance from the extreme end up to the section is x, and 2.5 kilonewton is acting at a distance of 3 meters from point A, from this extreme end. So this gap, this distance, the distance between 2.5 kilonewton load and the section is equal to x minus 3. And then last thing is this exposed moment m. If we rearrange this, we get m is equal to minus 2.5x minus 7.5. And for point B and C, if we plug in the values of x in this equation, we get mb is equal to minus 15 kilonewton meter and mc is equal to minus 20 kilonewton meter. So this completes our calculations for portion BC. How much was the value of bending moment for point B from point A side, from portion AB? If you look at the value of MB from portion AB, it is minus 15 kilonewton meter, and from portion BC, again we are getting the same value, minus 15 kilonewton meter. So it means that our calculations are correct. And there is another point to note here is that although we have a hinge support and there is no external moment acting at the hinge support, still we have some value of bending moment at this hinge support. So the statement or the point that we always say that at a hinge support, if there is no externally applied moment, then the value of bending moment will always be equal to 0. That thing is true for external hinge and external roller support. Now this hinge is not an external hinge anymore because we have an overhang present on the left side of the hinge support. That is why even though there is no externally applied moment at this point, still we have some value of bending moment at this support. Okay, so next is portion C. This is the free body diagram for portion CD. We have point A, B and C present on the left side of the section, and this time this moment is also included. We have the reaction of 2.5 kilonewton acting here. We have exposed shear and bending moment. The range of X is from 5 meters to 7 meters. Let's apply the conditions of equilibrium. Sigma Fy equal to 0 first. So 5 kilonewton force is acting in the downward direction. Positive 2.5 kilonewton is acting in the upward direction. Minus V is acting in the downward direction. This completes the equation for shear, and if we rearrange the equation we get V is equal to minus 2.5 kilonewton. Next, the equation of moment, sigma mx equal to 0. Starting from this side, 5 kilonewton force is producing moment in counterclockwise direction about the section. Minus 5x. Then this 2.5 kilonewton force is producing clockwise movement. So plus 2.5 into x minus 3. X is this entire distance and this 3 meter is this distance. So the distance between the load and the section is x minus 3. And then we have this 10 kilonewton meter couple acting in clockwise direction, and as it is a moment, so we do not need to multiply it with any lever arm, and it's acting in clockwise direction, so it should be taken as positive. And lastly, minus m, that is this exposed moment. If we rearrange this equation, we get m is equal to 2.5 minus 2.5x plus 2.5. Now if we plug in the value of x for point C and point D, we get the moment at point C equal to minus 15 kilonewton meter, and for point D, for point C we get minus 10 kilonewton meter, and for point D we get minus 15 kilonewton meter. Okay, so now let's move to the next portion, portion DE. Here is the free body diagram, the entire left part of the beam from the section that has been cut through the portion DE. The value of x ranges from 7 to 9 meters. So if we apply sigma Fy equal to 0, we have 5 kilonewton load acting in the downward direction plus 2.5 kilonewton force acting in the upward direction minus 5 kilonewton, and then this minus V, that's exposed shear, and that should be equal to 0. And when we rearrange the equation, we get V is equal to minus 7.5 kilonewton. And then the equation of moment, sigma mx equal to 0, clockwise moment with the convention, clockwise moment taken as positive. So 5 into x, and this is producing moment in counterclockwise direction, so minus 5 into x. Then this 2.5 kilonewton force producing moment in clockwise direction, 2.5 into x minus 3, and then this 10 kilonewton force acting in 10 kilonewton moment acting in clockwise direction, so plus 10, and minus 5 into x minus 7. 7 is this distance between point A and 5 kilonewton load. So x minus 7 is the distance between the point load and the section. So 5 into x minus 7 minus m equal to 0. If we rearrange this equation, we get m is equal to minus 7.5 plus 37.5, and x is present in this equation. It means that the value of moment varies as the distance from the section changes. So for point D and E, when we plug in the value of X, we'll get the value of MD and ME. MD comes out to be minus 15 kilonewton meter and ME comes out to be minus 30 kilonewton meter. Now let's move to the last portion, portion EF. For portion EF, X ranges from 9 to 12 meters, and this is the free body diagram of the entire left side of the beam when we cut a section through portion EF. Exposed shear and bending moments have been marked, and this time both the reactions are present in the free body diagram. So if we apply sigma Fy equal to 0, we get minus 5 plus 2.5 minus 5 acting in downward direction plus 17.5 and minus V. This is equal to 0. So V comes out to be 10 kilonewton in this case. And then for sigma Mx equal to 0, when we take clockwise movement as positive, 5x with the negative sign is the movement due to this force because it's producing movement in counterclockwise direction. 2.5 into x minus 3. X minus 3 is this distance between 2.5 kilonewton force and the section, and then plus 10 because it is in clockwise direction, and then minus 5 into x minus 7 is the moment of this 5 kilonewton force, and then plus 17.5 into x minus 9 is the moment of this force, and then minus m. If we rearrange this equation, we get m is equal to 10x minus 120. And for point E and F, if you plug in the value of x as 9 meter and 12 meter respectively, we get the values of ME and MF. ME comes out to be minus 30 kilonewton meter. If we compare this ME with the previously calculated ME, it's the same, minus 30 kilonewton meter. And for MF, it's equal to 0. At point F, what do we have? At point F, this is a free end and there is no externally applied moment acting at point F. So the moment at F should be equal to 0 and we are getting it as 0. So that seems correct. Now the last stage is to draw shear force diagram, bending moment diagram and elastic curve. For that, we will consider the beam once again. So I have drawn the beam here, and then wherever we expect a change, at that point we will draw a guideline. So draw the beam and then draw the guidelines. And then plotting of this shear force diagram and bending moment diagram is merely plotting up of those values that we have already calculated. And shear force diagram and bending moment diagrams, both these diagrams are not very complicated in this case because we have just point loads and point movement. There is no UDL or VDL, so there was no question of convex up or concave up in this case. So just plot these values and you will get the shear force diagram and bending moment diagram. If you notice that the entire bending moment diagram for this case is negative, which means that the entire beam will hog. So I have drawn an elastic curve that is hogging, and one thing that we need to keep in mind is that the elastic curve must always pass through the support. So we have a support here and we have a support here, and the elastic curve is passing through these points. So this completes our discussion about this problem. So I will just stop recording here. Thank you very much.